Hello, my name is Jason Phelps, and in this presentation I will be discussing how to implement locally linear embedding in Python using the Scikit-learn library. A short demonstration will be done using handwritten digit data before giving an all-inclusive overview of the model hyperparameters, methods, and attributes. The handwritten digits data is comprised of 1083 samples of the digits 0 to 5. Each sample has been reduced to 64 features. To understand the relationship between these 6 digits, it can be helpful to visualize the data. This requires some method of feature reduction. For some perspective, we can start with a random projection and see that some structure exists to the data, but it would be difficult to cleanly separate any of the digit classes based on these two features. Pictured are a select group of feature reduction techniques with minimal tuning, including principal component analysis, linear discriminant analysis, and 3 variations of locally linear embedding. LDA seems to have the best performance, but has a distinct advantage in that it is a supervised technique and can take advantage of target values. Although standard LLE may add little value compared to PCA, the modified and Hessian-based versions provide some separable regions without knowing the target class. This suggests that manifold learning may offer improvements over PCA for certain clustering tasks, or as additional inputs in building an ensemble classifier. It should be noted that there is a computing cost associated with each of these techniques. On this data, LDA was 6 times slower than PCA, LLE was 25 times slower, modified LLE was 50 times slower, and Hessian-based LLE was 60 times slower. To implement LLE in Python is relatively easy. It comes as part of the Scikit-learn library, which is easily attained with a pip install, or comes as part of the standard Python data science stack installation Anaconda. The locally linear embedding class is part of the Scikit-learn manifold module. After importing it, we can create an instance of the LLE class and define the hyperparameters to be used during the training step. Here we set the number of nearest neighbors to 30, the number of output components or dimensions as 2, and use the standard LLE algorithm. Next, using the fit method, we can learn a manifold that fits the handwritten digit data. For manifold comparisons, we can use the reconstruction error attribute. In order to actually visualize our data on the new manifold, we need to project our data to it. This can be done using the LLE class's transform method. Now the transform data can be visualized. To simplify the presentation, a user-defined plotting function is used, whose definition can be viewed in the appendix. Pictured are the LLE projection of our data with the PCA projection for comparison. The LLE class has 12 hyperparameters that the user can define before learning a manifold, all of which have defaults. 4 basic ones are listed here and can get a user started. The number of neighbors to use to build the local linear embeddings, the number of components that will define the output manifold, a regularization constant, and the nearest neighbor algorithm to be used. Alternatives to the standard LLE algorithm can be defined. The modified algorithm uses multiple weight vectors in the local spaces to address an issue with regularization in the standard algorithm, not guaranteeing an optimal solution. Hessian-based LLE addresses the regularization issue by using Hessian-based quadratic forms to learn the local linear structure. Tolerance values can be controlled for the advanced algorithms independently. The number of parallel processes can also be controlled using the njobs parameter. Some more advanced hyperparameters are related to the eigensolver algorithm used for the local spaces. For those interested in reproducibility, the random state parameter can set the random seed when the RPAC eigensolver is used. Once an LLE instance has been defined with the desired hyperparameters, a manifold can be learned from data using the fit method. After fitting, the transform method can project the data onto the manifold and allow for further visualization or modeling. The fit transform method combines the previous 2 methods into a single step. The get and set params methods allow the user to store and retrieve previously learned manifolds. Once an LLE manifold has been learned, the embedding vectors, reconstruction error, and the nearest neighbors model are retrievable using one of the LLE class attributes. That completes the overview of performing locally linear embedding in Python. For reference, the appendix includes examples of 3 to 2-dimensional manifold feature reduction of an S-curve and a severed sphere. Also included as promised is the user-defined plot embedding function used to plot the handwritten digits data. For further information, I recommend visiting the manifold learning documentation on Scikit-learn's website. Thank you.